Hello everyone, Govanen I Inethnin Gilrandir. I am Gilrandir, and in this video I will begin my exploration of the night sky. I'm going to be looking at the constellations from a three-dimensional perspective. I've always wished when looking at the stars at night that I could see it three-dimensionally the way it really is. Eventually it occurred to me that the reason it just looks flat is because it doesn't have the familiar perspective cues that we get when looking long distances on Earth. Things like vanishing points, bluing, and that sort of thing. So it's necessary to create a framework in order to visualize it in three dimensions. That brings me to the box. This outlines a wedge of space containing the principal stars of the constellation. I've also included a projection on the back of the box to help relate it to the sky view. The first one I'm going to be looking at is Ursa Minor, the Lesser Bear, also known to us as the Little Dipper. It's traditionally represented by 7 stars, 4 of which are named, and 3 will use the Greek letter designations. I want to mention about the nomenclature. The stars with Greek letter designations should be called Eta Ursae Minoris, Epsilon Ursae Minoris, and Zeta Ursae Minoris. But in this video, I'll refer to them as Eta Umi, Epsilon Umi, and Zeta Umi for short. And here it is. Looking at Ursa Minor unfolded in its box gives a greater sense of its real spaciousness, and we can see what it actually looks like. Stars that appear fairly close in the sky can actually be quite distant, like Pherkad and Kochab right next to each other in the bowl of the Dipper, but very far apart in space. The same thing applies to Eta and Zeta. And on the other hand, when stars are relatively close in space, such as Eta and Kochab, naturally they will appear close to each other in the sky. Next, I've prepared a table of distances between each of the 7 stars, which we're looking at here. On the first row is simply the distance in light years from our solar system to each star. The second row is the distance from Eta Umi to each of the rest of them, and then so on and so forth. Looking at a little closer, the numbers running along the diagonal in the middle are the smallest, and then they get larger moving away from the diagonal towards the corner. This is because the numbers along the diagonal are following the path from the nearest to us outward in order to the most distant from us. I also have a star size chart showing the many different sizes of the suns with our own Sol for comparison. They come in a range of different colors, with some of them being single and some of them having companions. A couple of them, Kochab and the Polaris Primary, are just too big to fit on the chart, so I've made separate comparison drawings for each of them. Now it's time to take a closer look at the individual stars of Ursa Minor. And going back to the box, I've put in a trip outline to tour the constellation. It will start with Eta at 97 light years from Earth, move out to Yilden, then back to Kochab, which is not strictly in order from nearest to farthest, but it was easier to draw that way. Then out to Epsilon, on to Zeta, dodging over to Polaris, and ending at Pherkad at 487 light years out. First stop will be Eta Umi, which is about 2/3 bigger than our own sun, and it's a type F star, which puts it in the white to pale yellow color range. And I've made a little sunset scene here to sort of get a feel for what Eta looks like as a sun itself. It includes our own sun for comparison purposes, and this would all be on some imaginary Earth-like planet orbiting Eta. Next, I'll take the 90 light-year trip over to Yilden, where we'll take a quick look at that. This is similar to the situation we saw over at Eta. Yilden is also a single star with no known companions. Slightly larger than Eta, but a different color, Yilden is a type A star, making it a little bit bluish. I've made another sunset scene here, similar to the one at our first stop, and for the same reasons, to get a feel for what Yilden looks like as a sun. And you'll probably notice I've dragged along the same imaginary planet that we used at Eta. Now that was a pretty big job, towing an entire planet 90 light years along just to look at a sunset. I don't think I'll do that again. Moving along now to the third stop, I'll double back and make the 63 light year trip to Kochab. Sennabeleg, this is a big one. The second biggest one in this group of 7 we're looking at. Because it's so big, I've had to change the scale to get it to fit. You'll notice the comparison image of our sun is a lot smaller here. That would mean that the view we're getting in the sunset scene is farther out than Earth's orbit, probably about asteroid belt distance. The sunset background is an airless moon-like world. Going on now to the Epsilon system. Epsilon Umi is a triple star system with a giant yellow primary, a blue secondary about the same size as our Sun, and a small orange third star at a great distance from the other two. The first diagram here is a size chart showing all three of the Epsilon suns plus our own to the same scale, and including the orbits also at the same scale, except for the orbit of the small one, which is way too far away to show. Next is an orbital animation centered on the big yellow primary. This is actually only a representation. Since the orbital period is 39.5 days, I can't show it at the actual speed, or this would be a really, really long video. Also, I wasn't able to keep the scales consistent in the animation. The primary and orbit are at one scale, while the blue sun and Sol are at a different scale. Then I've got a couple of sunset scenes. The first one has the primary and blue sun together. This is set on a hypothetical desert world, more or less like Tatooine, and the comparison Sol is the same size as what I used at Kochab, so the planet would be the same distance out. The second scene is for Epsilon's distant third sun. Since it's actually smaller than Sol, I was able to use the same comparison size as at Eta and Yilden. This puts the imaginary planet at the same distance from its sun as Earth is from Sol, but that far from such a small sun, it will be a cold, icy, glacier-covered world. Zeta Umi will be the next stop, 46 light-years deeper into space. Here is a single sun, type A, making it a pale blue color. The sunset scene here is set on another imaginary desert world with some areas of patchy growth. Since Zeta is about 5 times as big as our sun, I've made the comparison image the same size as at Kochab and the Epsilon double. Now we'll jog over 110 light-years to Polaris. Now Polaris is also a triple system, like Epsilon Umi, but it's very different. While all three of the components are type F in the white to pale yellow color range, the primary is a variable star of the Cepheid type. The first diagram is a size chart again, showing the Polaris primary at the same scale as the orbit of Mercury and our own central star. It's followed by an animation of Polaris pulsating, still with the orbit of Mercury for scale. And then the third sun in the system is again at a huge distance from the other two, much too far away to show on the orbital animation of the inner suns. And this is the orbital animation. Once again, the range of sizes of the objects and orbits involved is too great to show everything at the same scale. The second and third suns are at the same scale as the image of Sol, while the pulsating primary is not to scale with anything else. All of the orbits shown are to the same scale, and the orbits of Saturn, Uranus, and Neptune show how big the Polaris inner system is. And like at Epsilon Umi, the animation is a representation. The actual pulsation period of the primary is about 4 days, and the orbital period is just under 30 years. After the orbital animation, I have a sunset scene for each of them. In the first one, I put an airless moon-like world in an orbit around the variable primary. At this distance, the comparison Sol is a tiny yellow dot that's easy to miss if you're not looking for it. It's over on the left side of the image, a little way above the surface. Because of its huge size, I've set it way out, just past the orbit of Jupiter. In addition to the pulsating primary, the secondary is included, varying in size as it travels around its orbit. Like the orbital animation, this sunset scene is a representation. The pulsations of the primary and apparent size changes of the secondary would not be visible in the couple of hours of a single sunset. This is an amalgamation of the changes seen over the course of the orbital and pulsation periods, which of course are not in sync with each other. The next scene, which is also a representation, uses a burnt-out cinder of a world placed at the asteroid belt distance, making the comparison Sol the same size again as at Kochab. Although this world is actually orbiting around the secondary component of the system, its sky is completely dominated by the gigantic variable, as it goes through spectacular changes in apparent size due to both the orbital path and its intrinsic pulsations. Finally, the third sunset scene takes place around the distant third component of the system. Here I was able to put the imaginary planet at our standard distance from the Sun, making the comparison sol the same size as it is at Eta, Umi, and Yildiz. Now we move on to the last stop, Pharkad. This is 160 light-years from Polaris and takes us 487 light-years away from Earth. Again, this is a single sun, and being more than 11 times as big as our sun, I've used the asteroid belt distance comparison image like at Kochab and Zeta. The sunset scene background is a gas giant kind of like Jupiter or Saturn. That will wrap it up for this video. It's included a brief look at the Little Dipper spread out in three-dimensional space, and a quick glance at each star individually to see them as actual suns. I hope you found this worth a few minutes of your time, and Nai Gilgalad Uivin Men, may there always be starlight on the path.